So I'm very happy to welcome Professor Rainer Hollerbach from the University of Leeds. Rainer received his PhD at the University of California, San Diego, and now he's Professor of Applied Mathematics at the University of Leeds. His research interests are on terrestrial and astrophysical magnetic fields, magnetohydrodynamics instabilities, numerical modeling, Taylor-Couette flow. He has received the James B. Massey Wayne Medal by the American Geophysical Union, and he's an expert on numerical magnetohydrodynamics. And today we have our second lecture of our second invited lecture for our Masters on Advanced Physics. And I'm welcoming Rainer, and please share your screen, and the floor is yours. Thank you very much.
Okay, well, thank you for the invitation, first of all. Okay, so can you see the proper screen there?
Yes.
Can you see my first slide?
Mm-hmm.
Okay, right. So that's what I want to talk about, magnetorotational instabilities in cylindrical Taylor-Couette flows. So as Kostas just said, my background is in geophysical fluid dynamics and astrophysical fluid dynamics, to a large extent, though, just general classical fluid dynamics. And I will approach this magnetorotational instability from this background of just classical fluid dynamics in cylindrical Taylor-Couette flows. I'll also say a little bit, though, about the astrophysical application of it. So that's the basic idea that we want to start out with. Then a little bit of the background here. The MRI was discovered originally by Velikov, as you can see, a very, very long time ago in 1959. He did it in exactly this Taylor-Couette context that I want to consider here. Then it was completely forgotten, literally for several decades, until Balbus and Hawley in 1991, they rediscovered what turned out to be exactly the same instability, except they considered it in an astrophysical context. They were specifically interested in what happens with astrophysical accretion disks. And in that context, the MRI turns out to be incredibly important. This paper by now has been cited many thousands of times, and Balbus and Hawley have been awarded all sorts of very, very prestigious prizes for this work. So that was certainly very, very impressive what they did there. Then after their astrophysical work, and then once people realized that, oh, actually, exactly the same instability had previously been considered in the Taylor-Couette context, people decided it might actually be interesting to do laboratory experiments with liquid metals on this MRI. And so, well, several groups simultaneously pretty much had that idea and wrote up some papers explaining how it could perhaps be done. In particular, the one that's most relevant to me is this one, Rüdiger and Zhang, 2001. And the reason this is particularly important to me is because Günther Rüdiger is a good friend of mine. I've collaborated with him for many, many years. So it's through him that I got interested in this whole MRI thing. And in particular, he was just talking always on and on about all these MRI experiments that he wanted people to do. And I gradually got interested in it, and I realized there were some difficulties with it, though. But then I got to thinking, well, what else could people try? And that's then how I had just through talking with Günther, I had this idea for what's now come to be known as the helical MRI. So we did that paper in 2005. And then we talked to this experimental group, Stefani, Gundrum, and Gerbert. These are liquid metal experimentalists in Germany. And as soon as we sketched out our basic idea here, they said, yes, we can build an apparatus like that. And if you look at the time here, we did the theory in 2005. 1 single year later, we already had at least a first prototype experiment. Well, obviously, after that, we then improved on that experiment. And in later years, we just made the apparatus better and better. And we'll see some of those results and see how these later experiments are better than the very first experiment. Then there's also some things that we can consider in terms of looking at absolute versus convective aspects of this HMRI. As you may know from general theory of hydrodynamic instabilities, this concept of absolute versus convective instability, that is an important idea in many different contexts. It also turns out to be relevant to the HMRI. So we did a little bit of theoretical work there. Then it turns out that you can also take a purely azimuthal field and you can generate instabilities with that. So we did some theory on that, and there's also experiments on that and fully nonlinear calculations. I won't discuss it here, but there's also a Taylor-Couette dynamo where you just switch off the externally imposed fields completely. That's also a very, very interesting idea. And we did some numerical calculations there. And then finally, very recently, we're discovering that you can also switch things around so that your flow, instead of having the negative shear that would be relevant for the classical HMRI, you can have a positive shear. And in just the right parameter ranges anyway, you can still have the HMRI existing there. So that's a little bit of an overview and background and some of the things that we did. So here we want to consider the magnetorotational instability then in cylindrical Taylor-Couette flow. So first of all, for those of you whose background is not fluid dynamics, what is cylindrical Taylor-Couette flow? Well, it's just you have these two nested cylinders like so, and both of them can rotate. So the inner one has a rotation rate omega inner, and the outer one omega outer. And of course, these two can be set to be different. So you have differentially rotating cylinders. And the question is, what sort of flow patterns can you get in the gap in between? And this is one of the most fundamental problems in classical fluid dynamics, because when Taylor did this in 1923, that was the very first time that a hydrodynamic stability calculation, a theoretical calculation, actually agreed with laboratory experiments. Before then, mathematicians had done various hydrodynamic stability calculations, but it didn't seem to have any connection with actual laboratory experiments. And the discrepancy was in fact so great that people were starting to wonder, is there maybe something wrong with the Navier-Stokes equation? Or are we misunderstanding the right boundary conditions? Why is it that our theory never seems to agree with the experiments? Well, when Taylor did what are now called Taylor vortices in exactly this geometry, and it agreed perfectly with the experiments that he also did, that's when people really believed, all right, yes, we are on the right track here. So this is really a very, very important problem in classical fluid dynamics. So what we want to do is consider the magnetohydrodynamic equivalent of this, where we take the fluid to be electrically conducting. So in a laboratory setting, it would just be some sort of a liquid metal. In astrophysical applications, of course, as soon as you take any gas and you heat it up enough, it becomes a plasma, and that is electrically conducting. So electrically conducting fluids are certainly very, very important in many astrophysical applications. So what do we have here then? Well, first of all, the basic flow profile that you get between the cylinders there is just of this form. If you take the Navier-Stokes equation and you say your boundary conditions are that and that for the rotation rates of the cylinders, and you ask yourself, what is the basic state flow profile that you would get? It is just that. And the question then is, what are the various instabilities that can arise that can cause that thing to make a transition to a different sort of state? So also, what sort of externally imposed magnetic fields could we have? Well, there's the bit indicated in blue here. That is just a constant axial field like so. And that would be easy enough to set up in a laboratory setting if you just have a whole bunch of external Helmholtz coils around your cylinder like so, then it's pretty easy to set up a uniform axial field like so. And the classical, what is now known as the standard magnetorotational instability, that the theory of that was done for the purely axial field there. As it turns out, though, as we'll see later on, that turns out to be very difficult to do laboratory experiments because it turns out the rotation rates that you need for a purely axial field are enormously high, and that causes all sorts of difficulties. So as I say, when Günther Rüdiger started getting me interested in this problem at all, and I gradually realized that, well, the incredibly rapid rotation rates that you would need for a purely axial field, those are going to cause problems. I just got to thinking, what other possibilities would there be? And well, it's not too difficult to figure out you could also have an azimuthal field like this. So that is the specific form of the azimuthal field. And how would you generate that? Well, suppose you have some long central rod on the middle axis there, and you just run an electric current down that, then just basic first-year physics tells you that is the magnetic field that you would get. So the question then is, can you maybe take some sort of linear combinations of these two fields to make the MRI appear at rotation rates less than what you would need for a purely axial field? One other important point to note about both of these fields is that both of them have curl being 0. That means the electric currents that generate these fields are really purely external. So for this one, you have an electric current in your external Helmholtz coils. For that one, you would have an electric current running down the central axis, but neither of these corresponds to you externally forcing electric currents to run right through the fluid. If you allow yourself to break this and you actually impose electric currents running directly through the fluid, that is also a very interesting problem. You can get so-called current-driven instabilities, but those are sufficiently different from what I want to talk about here that I'm not going to consider them at all. So that's the basic setup. Then we can start looking at some equations here. So here, first of all, are the linearized equations for the onset of instabilities. This is the magnetic induction equation for the perturbation field little b. This is the Navier-Stokes equation for the perturbation flow little u. And so the question is, can we get instabilities coming out of those equations there? Well, one interesting result that we can already derive from these, if you derive the associated energy equation. So what is energy? Well, for fluid flow, it would be basically the integral of u squared. For the magnetic energy, it's basically the integral of b squared. So in other words, to derive this energy equation from those original instability equations, you take the Navier-Stokes equation and you dot it with u to give you that term, and you take that equation and you dot it with b to give you that term there. And you also multiply that one by this parameter Hartmann squared. This is the so-called Hartmann number, and we'll see later on exactly how that is defined. Now, the interesting result that you get when you derive this energy equation is these two terms indicated in blue here. Those cancel out completely, and they do not contribute anything to your final energy balance. So in other words, these two terms, they allow you to convert energy back and forth between magnetic and kinetic energy, but they do not act as either a source or a sink of energy. So in other words, you can see the only thing actually driving instability here is the imposed differential rotation, your basic state flow U0. Whereas your imposed magnetic fields B0, well, they act as a catalyst and they allow you to have instabilities, and it's incredibly important to allow you to do this conversion of the energy back and forth. Otherwise, you could not have the magnetorotational instability, but B0 itself is not a source of energy. All of the energy comes from the flow U0. Okay, so now let's look at something called the Rayleigh criterion also. The Rayleigh criterion says a flow is hydrodynamically stable if the angular momentum increases outward. Whereas for the magnetorotational instability, what we have is a flow is magnetohydrodynamically stable only if the angular velocity increases outward and not just the angular momentum. And this difference between whether it's the angular velocity or the angular momentum that has to increase outward, that is incredibly important, because if you consider astrophysical accretion disks, they are in exactly this regime where one of them is decreasing outward, but the other one is increasing outward. So what is an astrophysical accretion disk? Well, if you have studied a little bit of astrophysics already, then you probably already know what an accretion disk is. If you're trying to form an entire star, let's say, out of some giant gas cloud, well, the cloud gradually starts collapsing inward on itself by its mutual gravity, but because inevitably it also has a little bit of angular momentum as it gradually contracts. Well, conservation of angular momentum means it has to rotate faster and faster, and ultimately your gas cloud just collapses into this so-called accretion disk, where instead of being a nice round cloud, it's a very, very flat disk, and the thing just rotates around and around, sort of like the rings of Saturn. Well, it's at that point that you have a problem, because you want this thing to actually accrete. You want the mass to accrete onto the central object, and you don't want it to be like the rings of Saturn that just go around and around forever, but they don't actually accrete and collapse down onto the planet. Or if you have something like a black hole, then, well, at that point, you already have a very, very large and massive central object, but then you can also have accretion disks around those. And if you look at things that we believe to be black holes and you see the X-ray emissions coming from those things, we know that they are actually accreting. So we know that the accretion disks around black holes, they do not simply whirl around and around forever. They are actually very efficiently feeding mass into that central object. And at that point, you have a little bit of a problem in terms of explaining how that accretion actually works, because if you ignored the presence of magnetic fields, then you would say we are in this situation here where the Rayleigh criterion applies, because after all, the angular velocity in an accretion disk, well, it's just a Keplerian rotation profile, at least if the central object has most of the mass. So you've already accreted enough stuff onto the central object so that virtually all the mass is contained in the central object, then you know the rotation profile of the accretion disk must be a Keplerian profile where the angular velocity goes like r to the minus 3/2. So that in particular decreases going outward. And the angular momentum, though, omega r squared, that increases going outward. So at that point, you would say, if this is the regime that you are in, then you would say the Rayleigh criterion applies, and the conclusion would be your accretion disk is stable. If it is stable, though, then there is no way really for it to do any accreting at all, because if the only mechanism to transfer angular momentum outward and have stuff actually accrete inward, if the only mechanism was just purely laminar viscosity, just easy estimates tell you that is many, many orders of magnitude too small. If laminar viscosity were the only mechanism to get rid of your excess angular momentum and transfer it outward, and therefore have accretion going on inward, at that point, even something as simple as just forming a star would take so many billions of years that here we are 14 billion years after the Big Bang, there literally would not be any stars at all yet, because you wouldn't have succeeded in accreting anything onto the central object. So we know that cannot possibly be the case. So that's where astrophysicists were speculating and saying, well, some people were saying the Rayleigh criterion is a purely linear onset result, and maybe there's just a nonlinear instability. Well, it's true, no one has ever rigorously proved that that's not the case, but no one has ever proved that it is the case either. So at that point, that is a somewhat hand-waving argument and just hoping for the right sort of miracle occur that you could get your accretion to occur after all. But that's when Balbus and Hawley had this insight that the entire Rayleigh criterion, as we will see in a moment also, as soon as you add magnetic fields, the Rayleigh criterion is basically irrelevant, and what you have instead are completely different criteria, and then you have this so-called magnetorotational instability, and that says that if you wanted your flow to be stable, it's not enough to say the angular momentum has to increase outward, the angular velocity itself would have to increase outward, and then you say, well, that's fine. In our accretion disk here, the angular velocity does not increase outward, so according to the MRI criterion, we can have instability. That instability will generate the turbulence that we need to have sufficiently efficient angular momentum transport so that our accretion disk will actually do what we need it to do and accrete stuff onto the central object. So that's basically why it turned out that the MRI is astrophysically so incredibly important. Well, here very quickly, just sketch where the Rayleigh criterion comes from and why it is not relevant once you add magnetic fields. So I'm not going to go through all the algebra here, just explain in words what we have. Suppose we have these two fluid rings here, indicated by red and blue. So the red one, well, it has a radius of R1, and it has, let's say, angular momentum 1. And similarly, the blue one is at radius R2, and it has angular momentum AM2. So then the angular velocities will be omega 1 and omega 2. Now, suppose we want to do this sort of fluid interchange here, where we have these two rings just swapping places. Now, if you do this interchange in a purely axisymmetric way, so you just let the inner ring expand and the outer ring contract, and you have them swap places like this, then purely hydrodynamically, you have angular momentum conserved not just globally. Globally, of course, angular momentum is always conserved, but you would have angular momentum conserved locally, because the only forces that act in this sort of interchange would be pressure gradient forces. And in an axisymmetric situation like this, the net effect of any pressure gradient forces is going to be 0. Oh, by the way, also, we're neglecting viscosity here. The Rayleigh criterion is an inviscid result. So in the absence of viscosity, if the only thing that is otherwise acting are pressure gradient forces, then angular momentum is conserved locally on individual fluid rings. So what that means is that even after all this interchange process, the red ring still has its original angular momentum, and the blue ring still has its angular momentum, but they have now interchanged their positions. So this one now has size R2, and this one has size R1. So their new angular velocities are given by those results there with the primed variables. Well, if I know the original angular velocities and I know the new angular velocities, it's easy enough to sit down and work out what are the corresponding kinetic energies. Well, I've ignored factors of a half m here, assuming that they both have the same mass m, and we can easily enough ignore those factors of a half m. So, and here's the bit where you have to just sit down and do a little bit of algebra. Here are the kinetic energies before, and there are the kinetic energies afterwards. So what is the change in kinetic energy in going from there to there? Well, there it is. The change in kinetic energy is what you have afterwards minus what you had before, and a little bit more algebra gives you that result there. Well, that factor there, because R2 is greater than R1, that factor is strictly positive. So whether this change is positive or negative depends on that factor there. And so what you can see is if angular momentum 2 is greater than angular momentum 1, that means the change in kinetic energy is positive, and that in turn tells you that the original configuration is stable, because the only way to go from here to here would be if somebody externally gives you this amount of energy that you need to go from there to there. Alternatively, if the sign here were the other way around, well, then the change in energy would be negative. That would mean the system could spontaneously go from here to here, and in the process it would release energy, which then shows up as the energy in the instability. So that is basically an outline of where the Rayleigh criterion comes from. And at this point, we can immediately also see why it is simply not relevant once you add magnetic fields. As soon as you add magnetic fields, so imagine that there's all sorts of magnetic fields threading this whole system. Well, we know what magnetic fields do. You have the Lorentz force, which can be thought of as a magnetic tension in the field lines. So imagine that you have magnetic fields threading this whole system. Then you see different fluid rings are coupled to each other via the magnetic fields and the tension in the field lines, and therefore you can transfer angular momentum from one fluid ring to another. So this original assumption that angular momentum is conserved individually on individual fluid rings, as soon as you add magnetic fields, that simply does not apply anymore. And that is why the Rayleigh criterion is not relevant as soon as you add magnetic fields. So what do you have instead for the MRI? Well, here are the same linear stability equations that we saw before. Here's just the details of how things got non-dimensionalized. For a length scale, it's pretty natural. Take, let's say, the radius of the inner cylinder, time the rotation rate of the inner cylinder, and, well, that's natural things then for the fluid flow. For B0, well, since that's externally imposed, that's a natural scale for that. For the perturbation B, that turns out to be a useful scale there. So that's how these equations were non-dimensionalized, and the non-dimensional parameters that then appear in the problem are the magnetic Reynolds number there, the ordinary hydrodynamic Reynolds number there. I hope these are familiar to you if you've studied a little bit of astrophysical fluid dynamics before. Certainly this is very, very familiar to anyone who's done fluid dynamics before. And you can see this one, why it's called the magnetic Reynolds number, because it has the same sort of form, except instead of the viscosity in the denominator here, it's the magnetic diffusivity, eta, in the denominator there. Then we have the magnetic Prandtl number, which is the viscosity divided by the magnetic diffusivity, or also it's the ratio of the two Reynolds numbers. And because these quantities, viscosity and magnetic diffusivity, those are each just material properties of your fluid, that means that your magnetic Prandtl number also is just a material property of whatever fluid you choose to use. So in particular, if you're doing laboratory experiments with liquid metals, well, then you just have to go and look up what is the magnetic Prandtl number of your liquid metal. And it turns out all liquid metals have very, very small values for PM on the order of 10 to the minus 5 or 10 to the minus 6 or even smaller. And that will turn out to have important consequences. And finally, the Hartmann number there is a measure of the strength of your externally imposed magnetic field there. So what do we have then? Well, suppose we start with the classical problem, what's now known as the standard magnetorotational instability, where we take our externally imposed field to be this purely axial field like so. So then we go back here to our stability equations, and we want to do an analysis on them. So we're going to do separation of variables, and we look for modes that have a periodic structure e to the I kz in the axial direction, and they have an exponential dependence in time. So we're going to want to look for something that's exponentially growing ultimately. You notice also that I have no dependence on phi. So at the moment anyway, I am looking for axisymmetric solutions. That means that I can decompose little u and little b in this sort of a form. This is called a poloidal toroidal decomposition, or also that and that are called stream function representations. And that means I've automatically taken care of div u and div b being 0. Well, if you do that, and then you go back to these equations, for this equation here, you want the phi component of that equation and the phi component essentially of the inverse curl of that equation. For this equation, you want the phi component of the equation and the phi component of the curl of that equation. And that ends up giving you those 4 equations there. So there's the phi component of the Navier-Stokes equation. There's the phi component of its curl. There's the phi component of the induction equation. And there's the phi component of the inverse curl of the induction equation. And you can see your separation of variables approach that really worked. And everywhere you had z derivatives, you just have factors of ik, that d squared is basically a Laplacian, and there's a d to the 4th. And what were the time derivatives on the left side of the equations give you those factors of gamma. So the whole thing has been reduced to a linear one-dimensional eigenvalue problem. There's only the radial structure still to be worried about. Well, at that point, numerically, you can do various different things. Günther Rüdiger, for example, he solves things by doing finite differencing in the radial direction. I prefer to set things up by doing expansions in Chebyshev polynomials in the radial direction. well, it's just as well that we have two completely separate codes for doing these things, and we can easily enough benchmark our different results against each other and make sure that we really set everything up correctly. So what do you get in that case? Well, suppose we fix that as our radius ratio, and we fix that as our rotation ratio, and that is carefully chosen to be in the analog of that regime that we would have for the astrophysical accretion disks. That is, the angular velocity, as you can see, is decreasing going outward. Omega outer is less than omega inner, but the angular momentum is increasing. So this is the analog that we want, that's most relevant for the astrophysical accretion disk problem. So what do we get? Well, plotting on this axis the Hartmann number, and on that axis the Reynolds number, then we just do the numerical calculations for these equations here, and we see how do you have to set your various parameters, the Hartmann number and the Reynolds number, and well, we'll see in a moment, we just fix certain values of PM, K, the axial wave number, well, that the system is allowed to pick that itself, so that's not a parameter that you externally get to fix, so you have to optimize over K and allow the system itself to pick the preferred value of K. So you do lots and lots of calculations to do the optimization over K, and you get these instability onset curves like so. So for PM equals 10 to the minus 5, then you would find that Reynolds number there of 10 to the 6 or so. That would be how rapidly you have to rotate your system to have any chance of having the instability. If you choose a different liquid metal that has PM of 10 to the minus 6, then you can see your critical Reynolds number shifted up even more. So now you have to rotate the speeds so that you have a Reynolds number of 10 to the 7. And there you can see things are starting to get problematic because the Reynolds numbers are starting to get very big. Well, one thing you can notice also, these two curves here, the shapes are basically the same. They're just shifted relative to each other. So that suggests that maybe your parameters, Hartmann and Reynolds, are not really the right parameters. Instead, we want to do the following thing. We have this thing, it's called S, the Lundquist number. That's how we want to measure magnetic fields. And how is S defined? Well, S is this quantity. It's Hartmann times PM to the half. And where does that come from? Well, we just look at that. We notice shifting from there to there, it shifts. The critical Hartmann numbers seem to scale like that. So that what suggests to define a new quantity like that. And once we have that, we realize, oh, this is actually a familiar quantity, the so-called Lundquist number. Similarly, the Reynolds numbers, well, we've already seen, if you decrease PM by a factor of 10, that shifts upward by a factor of 10. So the Reynolds numbers scale like that. So that suggests that the relevant parameter is really not the Reynolds number, but the magnetic Reynolds number that we saw before. So on this diagram, S on that axis and RM on that axis, everything just collapses like so. And these are the critical values for the onset then of the MRI. In terms of where these scalings come from, it's, if we go back to our equations, the important one to look at is this one here for that quantity there, little b. And the relevant factor there is this one. Unless that factor there is sufficiently large, you cannot get instability. And because that Reynolds also has that factor of PM sitting in front of it, that's why the relevant scaling is really not RE by itself, but RE times PM, which gives you that. Okay, so, well, as we saw, the purely axial field, that forces you to have very, very large Reynolds numbers, which turns out to lead to various technical difficulties. It's just an engineering challenge to build something that can rotate as rapidly as that and still control things at the end plates of your cylinders. So that's where I just got to thinking, well, what other possibilities are there? And so that's where I thought, well, we can always add in any linear combination of that azimuthal field. And well, I had no idea what would come out in advance. One thing I knew is that the same separation of variables approach would certainly still work. And the only thing you would have is that you add a few extra terms coming from that extra bit added to B0. So you sit down and work it out, and it's only 2 extra terms that get added to your equations. It turns out, though, this one in particular is absolutely crucial to add that term in. And in particular, what do you get now? Well, this is a rather complicated figure. To understand this, let's go back maybe to this. You notice here I've computed everything in the entire Hartmann-Reynolds number plane, and I've drawn out the entire instability curve. Suppose we focus only on that bottom point. So that is now optimized over all possible Hartmann numbers. What is the smallest Reynolds number where you can still get an instability? That is what we're showing here. So optimized over all possible Hartmann numbers, what is the smallest critical Reynolds number that you can get? And now we are also showing the entire range of that rotation ratio, omega outer over omega inner. So what we had before, there we were at 0.3, and we were in the case where beta, the added azimuthal field, is 0. So we were either there for the 10 to the minus 5 or there for the 10 to the minus 6. So now you can see, well, if you have the previous purely axial field, then sure enough, you get these incredibly large Reynolds numbers over pretty much the entire range of rotation ratios until you get to this point. Well, in this regime here, you have already purely hydrodynamic instabilities, just the onset of non-magnetic Taylor vortices already. So that's not what we want. We definitely want to be in this regime where we are beyond that critical value where you would not get non-magnetic instabilities and you would only have the MRI regime. So to be in the MRI regime, we definitely need to be to the right of that value. And there you can see, taking beta equals 0 basically doesn't work, because as soon as you're just the tiniest little bit to the right of that, you immediately go shooting up to these very, very large Reynolds numbers there. You can see, though, as soon as you add in a little bit of an azimuthal field, beta equals 1, this thing just becomes flatter and flatter and flatter. And, well, you can see 2 things happen. First of all, the critical Reynolds numbers become literally orders of magnitude less than what they were before. And also, instead of having this 1 over PM scaling that we had there and there, the curves become independent of PM, and 10 to the minus 5 and 10 to the minus 6 give you exactly the same results. Oh, wait, let's just have a look and see where it came from again. Again, it's this equation here, and it's this term right here. And what this term does, this term essentially takes over the role that was previously played by this term, right? Remember, we agreed before, the reason that the Reynolds numbers have to be so large is because PM is so small, and this term is simply critically important to drive your instability. Well, if you now add that extra term in there, then the role that was previously played by this term gets taken over by that term, and then the dependence on PM is just completely different. Well, here is the instability patterns, what the actual spatial structures of these things look like. And one important point to note is that unlike, well, either non-magnetic Taylor vortices or also unlike the standard MRI, which are just stationary patterns that sit there in space, this so-called MRI, it drifts in the axial direction. So the entire pattern just drifts upward or downward. And there's a reason for that. It's because when you add that azimuthal field, the previous up-down symmetry in the problem gets broken. And as soon as there is a difference between up and down, well, generically then you would expect the instabilities to drift. So that's why generically in this situation, you expect any instabilities to have some sort of a drift in the axial direction. And that also turns out to be important because it's exactly this sort of drift that forces you to address questions like the difference between absolute versus convective instabilities. Well, time is definitely ticking, so we better move on. And so here is the experiment that we set up then. So there is the basic experimental setup. You can see it's some sort of a vessel like so. The liquid metal gets poured in the top there. It's gallium indium tin is the metal that we chose. Then the inner cylinder is this sleeve-like thing that slides in like so. So we can differentially rotate the thing, but because the fluid is contained in this bucket-shaped thing there, we don't have to worry about fluid leaking out the bottom. Then there are the Helmholtz coils that generate the axial field, and there is the rod that goes into the central axis to generate the azimuthal field. Oh, and there are these things called U. These are ultrasound transducers that they send out a little ping, and from the Doppler shift of the reflected signal, you can measure then the axial component of the velocity as a function of depth and time, and that is how you can then see what's actually going on inside that. Otherwise, obviously, you can't look inside that setup, and a liquid metal, you couldn't look inside that anyway, but with these ultrasound transducers, you can actually look inside effectively and see what is happening. Well, here are various upgrades that we made in going from our original crude prototype to the later things. Again, I don't want to spend time on all of this. The most important thing is in the original thing, we had the upper lids. They were simply fixed in the laboratory frame. They were not co-rotating either with the outer cylinder or the inner cylinder. So we knew that's going to have massive disruptions at the upper boundary. In the improved setup, we had this split ring configuration where part of it co-rotates with that, part of it co-rotates with that, and that really does have enormous improvements. In particular, let's see here then. Well, here again is our same sort of instability plot. First of all, the theoretical lines. Here we're plotting the axial field on that axis and the azimuthal field on that axis. And there are a few contour lines then for what the critical Reynolds numbers would be. The dashed line here corresponds to fixing the Reynolds number at that particular value where we did the experiment. So in particular, you can see then, if we look at this sequence of the red dots, that would say you're switching on the instability. You should have no instability, then you switch it on. Whereas if you do the sequence of the green dots, then you're switching off the instability there. One other point to note, the azimuthal field measured on that axis. On this axis are what are the actual currents down that central rod that you need to generate those sort of fields. Well, there they are in kiloamps. So you can see you need several thousand amps down that central rod. So this is not a trivial experiment to do, and that's why that rod also had to be, that's why that rod had to be as thick as that, and even then you needed some massive cooling on that rod so that it doesn't get too hot when you run several thousand amps down that rod. Okay, so here is what you get with your ultrasound signal then as you gradually switch on the MRI. So here at 5,000 amps, well, we get a little bit of something. Then at 6,000 and at 7,000, we have a definite signal. So this is now depth along the cylinders there and time there. So sure enough, we can see some sort of structures that drift upward. And from these patterns, we could measure a wavelength to these things. And from the slopes of these lines, we can measure the speed and we can do theoretical comparisons, and they look generally good with the theory. Here also for comparison, this is what we got with our original crude prototype, including all the problems that we had at the upper end plates, whereas this is how clean things look with the later experiments. And you can see, sure enough, this looks a lot nicer than that. It's even better if we look at the next one, where we want to switch off the MRI again. Here we still have it. Then we increase the axial field, and we can really completely switch it off. Whereas in the original crude apparatus, this is how much noise we still had left over, even after the instability was supposedly switched off. So all those various upgrades really enormously improved the situation. Well, I'm running out of time, so let me skip all this absolute versus instability stuff. This is the paper anyway, if you want to read about that stuff. Okay, so here's another interesting thing that we can do. Suppose we take a purely azimuthal field. Now it's known in this case that you cannot get any axisymmetric instabilities, but you can still look for non-axisymmetric instabilities. So we did that. We looked for an m equals 1 non-axisymmetric instability, and we got the same sort of pattern that we had before for the helical MRI. Again, if you're too far out here, then you get this awkward fact that the Reynolds numbers scale as 1/PM, which means experiments in this regime are extremely difficult to do. But if you're willing to settle for being in this regime here, where you're a lot closer to that limiting Rayleigh value there, then the critical Reynolds numbers are much, much less, and you can hope to get instabilities there. Here is what the instability curves look like. And now we can also say, suppose we took our purely axial instability, and we want to see what happens if we gradually add in a little bit of axial field after all. And in particular, we want to see at what point do you get the transition back to the helical axisymmetric instability that we had before. Well, as soon as you add in a little bit of that, then you also have a symmetry breaking between left and right spiraling instability modes. So you can think of them as either m equals plus or minus 1, or you can fix m equals 1 and have k take either positive or negative values. Either way, physically, they're just left or right spiraling modes. And if you have just that tiny little amount of axial field added back in, then, well, that dashed line is the original bit with delta equals 0, where the left and right modes are equivalent. So if you've broken the symmetry just a tiny little bit, or qualitatively it's still basically the same, then increase delta a little bit more. The left and the right modes shift a little bit more between each other. That mode labeled 0, that is the axisymmetric helical mode coming back in from before. By the time you get to delta equals 0.4, from a general nonlinear dynamics point of view, this will be a very interesting regime to do numerical calculations, because there you can see you have 3 distinct modes that are all onsetting at very, very similar values. So there could be lots of interesting mode interactions in the nonlinear regime. By the time you get to even just delta equals 0.5, the original axisymmetric HMRI mode is already preferred over both of those non-axisymmetric modes there. So this is what the modes actually look like, the left and the right spiraling modes. But again, since I'm running short on time, let me skip the details there. There also, we did some experiments with that, but let me again skip that. So we are coming to my last few slides here. Suppose we want to just do the full nonlinear equilibration of some of these problems. So fully 3-dimensional calculations. And this is work where Anna Guseva, she was a PhD student, and she was really amazingly good. She developed this big, complicated, fully 3-dimensional code, and she parallelized it and everything. And we did lots of calculations there. And you can see these are the sort of resolutions that we had. So hundreds of points in the radial direction, hundreds of Fourier modes in phi, and hundreds of Fourier modes in the axial direction z as well. So we did lots and lots of fully 3-dimensional calculations. And here's just some sample solutions showing some of the things that she did. And this is also the case where we did this interesting dynamo calculation, where we just said, what happens if you take one of these solutions, let's say, that you get by having an externally imposed magnetic field? What would happen if you just switch off that externally imposed magnetic field? Can you still maintain some sort of a turbulent dynamo solution, or would everything just collapse back to the purely laminar basic state? And it turns out, yes, you can actually maintain a turbulent dynamo solution. So that, of course, is also of enormous interest to the astrophysics community. So this, well, I'm not going to just briefly mention the existence of these results, but don't really have time to go over any details. So everything that I said before, everything about all of these various MRI variants that we had before, they were all in this case where the angular velocity decreases going outward. And all of that, we considered that because that is the case that is most relevant to that astrophysical accretion disk problem. Well, certainly just from the point of view of classical fluid dynamics, you could ask yourself, what happens if we just reverse that and we have the angular velocity increasing going outward? So in particular, suppose we have our inner cylinder completely stationary and we rotate only the outer cylinder. So in the non-magnetic situation, the Rayleigh criterion would again say this situation should be completely stable and nothing ever happens. Can we still maybe destabilize this by adding magnetic fields? And it turns out, yes, it's more delicate than the MRI modes that we had before. That is, you have to pick where you are in parameter space much more carefully than before. But if you find the right regime in parameter space, you can get instabilities occurring even in this case. So we are, well, you can see, we only just discovered these modes relatively recently. So we haven't really yet begun to explore the nonlinear equilibration of these modes. but there's certainly interesting things to be looked at there as well. And possibly, there could possibly be at least some regions in the interiors of stars, for example, where this positive shear regime might actually be relevant astrophysically as well. So we are, I'm basically out of time, and here are my conclusions also. So the first point to note is, even though it's a very simple problem, and ultimately it's just a linear one-dimensional eigenvalue problem, the parameter space is enormously big though, because you have 6 different parameters that you can adjust. You have the 2 rotation rates of your cylinders, you have 2 possible choices of fields that you can impose, you can adjust the basic geometry of your cylinders, and you can adjust the magnetic Prandtl number of your fluid. So in that 6-dimensional parameter space, that is so incredibly vast that even just the linear onset is not necessarily fully explored yet. There could possibly still be completely unknown instabilities out there somewhere. Then for most of these modes, we haven't really looked at the nonlinear equilibration at all yet. Then at least some of these modes, especially all the various MRI ones in that regime that are relevant to astrophysical accretion disks, those really are astrophysically interesting, even if you're studying them in something as simple as this idealized Taylor-Couette geometry. And finally, let me just say, just 2 years ago, we wrote this review paper, and you can see that thing is 89 pages long. So that's how much stuff there is to talk about just instabilities in Taylor-Couette geometry. This paper also includes all of these so-called current-driven instabilities. So not just all these MRI modes that we had here, but all these other modes as well. So I think I will stop there. Thank you.
Thank you very much, Rainer, for this very nice talk. It was very informative and very interesting. I don't know if anyone from the audience would like to ask some questions. People decided not to interrupt you, so probably they will ask questions at the end.
I have a question, Kostas.
Yes, please.
I'd like to ask what defines in the experiment the wavelength of the instabilities that you see?
That's a good question. Well, as I say, the wavelength of the instability is not something that you get to impose on the system. The system itself decides what wavelength of instability it wants to choose. So when you're doing the numerical calculations, you certainly have to optimize and allow for all possible Ks and pick out the most unstable one. So when we did the numerical calculations, we had a prediction in advance as to what the wavelength ought to be. And when you go and, well, even just when you build your experimental apparatus, so for example, when we look at this apparatus here, why did we decide to build this apparatus as tall as that? Well, you certainly have to build your thing tall enough to allow at least a few wavelengths of your basic pattern to appear in the gap. And if you look at our experimental results here, you can see, well, let's look at this one, for example. You can see we don't really have very many. If you look at a given cut like that, we have barely maybe 2 wavelengths of the pattern. So what that is telling you is that ideally, it would have been nice to build this entire apparatus 2 or even 3 times as tall. At that point, of course, it just becomes increasingly difficult because you can imagine even just building this apparatus was not so easy. And I forget how much this apparatus weighs, but this thing is already very, very heavy. This fluid in there, this gallium indium tin, that stuff has a density something like 10 times the density of water. So just the weight of this apparatus alone is quite a lot. So if you tried to build something 3 times as tall, then there are all sorts of engineering challenges in there. But yes, absolutely, you need, before you sit down and build this apparatus, you need at least some idea of what wavelength of instability are you going to expect, and you better make your apparatus big enough that there is room in there for, well, at least 1 or 2 wavelengths. And yeah, we did the absolute bare minimum here.
All right, thank you. Panagiotis.
Thanks for your nice talk. My question is a little bit more in an astrophysical context. So let's consider a binary neutron star merger. The initially weak magnetic fields can be significantly amplified due to the rise of the MRI instability from maybe 1 to 3 orders of magnitude. And this is something that can suppress the differential rotation of the compact remnant that is the result, and therefore leading to a uniform rotation. And this has important implications for the observations, especially in gravitational waves. So I was wondering, since it is very difficult to capture accurately the full extent of the MRI in numerical computations, maybe are there any ways that we can go back to the experiment and maybe get some new ideas as to how to work around this problem?
I'm not quite sure. I mean, you were saying that the magnetic fields are amplified by several orders of magnitude.
So yeah,
as soon as you're talking about amplifying magnetic fields, it's not really strictly the MRI anymore that you're referring to. At that point, it's just a dynamo. Well, either it's a dynamo or it's just purely compressional amplification of the magnetic field, right? If you take a very big star and you collapse it down to a neutron star, just that compression alone will enormously amplify magnetic fields. But the whole theory of the MRI basically says, imagine that you have an externally imposed magnetic field, and can that destabilize for you a fluid flow that purely hydrodynamically would be stable? So if you have all these other things going on, which are already driving turbulence, and that turbulence is so vigorous that in fact it's already acting as a dynamo, then I think in a lot of ways that goes beyond just the basic MRI.
So it's a much more complicated picture.
I think so, yes. Yes, that's much more complicated.
Yeah, okay, thank you.
Thank you. I don't know if there are any other questions that people would like to ask. If not, I have a couple of questions. The first one is related to a problem that we have been studying recently with Sergey, and it was the kind of opposite of MRI in the sense that we are having a flow. It's not a Taylor-Couette flow that is unstable subject to the Rayleigh criterion, and there with a sufficiently strong axial magnetic field, we have been able to stabilize the flow against the Rayleigh criterion. And I was having, and I have found this a bit confusing, if there is a way to reconcile this with the MRI instability. So is there a study of what the equivalent of MRI would be if also the Rayleigh criterion is not satisfied? Or you believe that the flow, the fluid instability dominates the problem?
That, I mean, in a sense, when Velikov first discovered the MRI in the Taylor-Couette context, people were surprised by that because it was the exact opposite of what they expected. People expected that magnetic fields would generally have a stabilizing influence because of the magnetic tension in the field lines, essentially. That magnetic tension strongly resists, it does not want the field lines to be distorted. So things like classical non-magnetic Taylor vortices, the expectation was magnetic fields should suppress all of that. And sure enough, they do. That's what Chandrasekhar already wrote about in his book. And Donnelly also did some experiments right around that time that Chandrasekhar wrote his book. Donnelly did some experiments using mercury, and he found, sure enough, you can suppress the previous non-magnetic Taylor vortices by just adding a magnetic field. So that certainly is absolutely true. Magnetic fields will suppress all sorts of non-magnetic instabilities, and that was the expectation before. So, and I think that is true in general. If you have an instability which does already work just fine even without any magnetic fields at all, it probably is true that adding a magnetic field to that configuration, the magnetic tension will probably tend to suppress that. So the special thing about the MRI is it works in this regime where non-magnetically nothing at all happens. And then you get this weird and counterintuitive result that even though you think magnetic fields should have a stabilizing influence, and now you're adding them to a situation which is already stable before, and all of a sudden you get an instability.
Right. Right. Thank you very much, Rainer. I don't know if anyone would like to ask any further questions for Rainer. If not, let's thank our speaker again. And we are looking forward to see you in 2 weeks' time for our last seminar for this term. Rainer, thanks again for visiting us in Patras remotely, and we hope after that you will come in person and get out to dinner as we normally do with speakers.
I hope so. It would be nice, yes. But yeah, this is already nice just to have a little break from sitting around at home in quarantine, just talk about science and see some familiar faces. It's nice, so thank you.
It certainly is. Thank you very much.